We are in Chapter 4, Part 2, Additional Applications, Exponential Models. The first example says, find the x values of all points where the function defined as follows have any relative extremas. And then it says to classify the x values as a relative maximum or minimum. So the first function that we have here is 3x e to the x plus 2. So in order to find our maximums and minimums, any relative extremas, we need to take the derivative of our function. And so since the first term that we have here is multiplication of two parts that have variables, we need to use the product rule. So it's going to be the first term, which is 3x. The second term is e to the x. We have 3x times the derivative of e to the x is just e to the x plus e to the x times the derivative of the first, and the derivative of 3x is just going to be 3. And then again, the derivative of 2 would just be 0. In order to figure out where we have our maximums and minimums, we need to take our derivative and set this equal to 0. And so we can factor out both a 3 and both an e to the x. And we are left over with x plus 1. Since we're multiplying here, we can use the zero product property and set each of these equal to 0. Dividing the first one by 0, we have e to the x equals 0. And then in order to solve this, I'm going to go ahead and take the natural log on both sides. And when we go through and take the natural log on both sides, we are going to end up with x is equal to, and we cannot find ln of 0. This is undefined. Remember, from the domain, you're only able to take logarithms of something positive, so that's not going to actually solve anything for us. However, we do arrive at x is equal to -1. So this is going to be our critical value, which is also probably going to be a relative extrema. And in order to figure out what this is, I'm going to draw a number line. And our domain for our function that we were given up here is all real numbers. And the reason why it's all real numbers is because an exponential is all real numbers, and also x is all real numbers. So that would, multiplying those together, we still have all real numbers. The only value that we have here is x is equal to -1. So I'm going to go and put that on. And I need to test something smaller than -1. And we'll just go ahead and say -2. Something larger than -1, we'll say 0. And so substituting these into your derivative, which is simplified, and right here I'll box that. When substituting in -2 into 3e to the x times x plus 1, we arrive at a negative answer, and that means that since we're substituting that into the first derivative, that tells us that our function is decreasing on that interval. Next, if we substitute in 0 into 3e to the x, x plus 1, which is our derivative, we have a positive answer, which means that that is increasing on that interval. So this changes from decreasing to increasing at -1. So that means we can classify this x value as a relative minimum. So we have a relative min. And again, this was only asking for the x values. X equals -1. If you needed to find the y values, you can substitute this into the original equation that you have, f of x, in order to get our y values. The second one that we have is f of x equals x squared divided by ln of x. So again, it's asking for the same directions as the one before. And so for this, it's asking for us to figure out if we have a relative minimum or a relative maximum, and just listing those x values. So in order to do that, we have to take the derivative, and this time we have a logarithm involved. I also have a numerator and a denominator, so when I find my derivative, I'm going to have to use the quotient rule. So the quotient rule is going to be the denominator times the derivative of the numerator. Derivative of x squared is just 2x minus the top times the derivative of the denominator. The derivative of ln of x is 1 over x. And then it's the denominator squared, which goes in our denominator. From here, we can clean this up a little bit. We end up with 2x ln of x minus one of those x's would simplify out or reduce, minus x all over ln of x quantity squared. And also looking at our original function, this time we don't have a domain of all real numbers. Our domain here, since we are dealing with logarithms, and logs are only allowed to be taken of positive values, we can say that we have x such that x is going to be positive, so greater than 0. So we say that x such that x is greater than 0. However, we have another issue with our domain. The denominator is also not allowed to equal 0. And so if you were to solve this, you have log base e of x cannot equal 0. And so we have e to the 0 is equal to x, rewriting that in exponential form, and e to the 0 is just 1. So we know that x cannot equal 1. So our domain is going to go from, and you can also write it this way, x such that x is greater than 0, and I'm going to put comma, x cannot equal 1. Since again, that makes the denominator be 0. So from here, multiplying both sides in my derivative by ln of x squared, I arrive at 2x ln of x minus x is equal to 0. I can factor out an x, and I'm left over with 2 ln of x minus 1 is equal to 0. I can separate these by the zero product property and say x is equal to 0 and 2 ln of x minus 1 is equal to 0. Solving the first one is solved already for me. However, 0 is not in the domain. So go ahead and ignore that one since it's not in the domain of our original function. And then for the second one, if I add 1 and divide by 2, I have ln of x is equal to 1/2. And again, rewriting this as log base e of x equals 1/2. I can rewrite this in exponential form as e to the 1/2 is equal to x, and this is approximately equal to 1.65. So I'm going to go ahead and draw my number line, and again my number line is only going from 0, which we're not including, through infinity, but also keep in mind that we are not able to pick 1 because 1 is a value that is not in my domain of my original function. And so the only critical value that we have is e to the 1/2, which is approximately 1.65. So I'm going to go ahead and substitute in something smaller than 1.65, again not selecting 1, and I'm going to go ahead and say let's substitute in 0.5, and then something larger we can substitute in 2. So substituting in 0.5 into my derivative I will go ahead and box up here. That was our simplified derivative. When I substitute that in, we arrive at an answer that is going to be negative, and that means that this function on this interval is decreasing. And then it switches, and when we substitute in positive 2, we arrive at a positive value, and that's going to be increasing. So this function is decreasing and switches to increasing at e to the 1/2. So that means we're going to have a relative minimum at x equals e to the 1/2. So they usually want the answers to be exact unless otherwise stating to round a specific value. And again, if you wanted to find the y value, you can substitute e to the 1/2 back into that original typed problem in order to get it. The next example that we have on page 9, we're going to go ahead and circle it, and we'll work on that one together in class. The graphs at the top of the next page show exponential growth and decay. If you notice, the growth graph is growing as you go from left to right, and the formula for this has k, which is part of the exponential exponent, is greater than 0, and then decay, our k value is less than 0, and it is declining as time goes on or as we read the graph to the right. So the next example that we have says Josie is a marketing manager, and she determines that sales of a particular commodity produced by her firm will decline exponentially once an advertising campaign for the commodity is terminated. Josie finds that the sales level is 21,000 units at the time the advertising ends and 19,000 units after 5 weeks. Round our answers to 2 decimal places. So part A says find S naught and K so that S of T equals S naught E to the negative KT gives the sales level T weeks after the advertising campaign ends. What sales level should Josie expect 8 weeks after the advertising ends? So first of all, they give us the amount of units that were sold as soon as that advertising campaign ended. And so S of 0 is equal to 21,000. And we also know after 5 weeks, and since we're measuring this in weeks, it'd be S of 5 is equal to 19,000. So we are able to leave these this way. I'm going to go ahead and erase all of my zeros here for both of them. And just say that these are both going to be in thousands. Makes it a lot easier to deal with rather than dealing with really large numbers. And again, this is when T was equal to 0. And this is when T was equal to 5. And again, we're measuring in weeks. So from here, we know that S of 0 is equal to S naught E to the negative KT, which is what we are given up above. Go ahead and circle that for us. And as stated here, I put down T is equal to 0, so I'm going to go ahead and rewrite this with T as 0. And we know S of 0 is 21, and again, we're dealing with in thousands, but we left it that way. S naught, and then E to the 0 would just be 1. So solving this, we get S naught is equal to 21. That's again our initial amount. So from here we have a formula. It's going to be S of T is equal to 21 E to the negative KT. And so now I'm going to use my 5 with my 5 weeks to figure out what K is. That's the other variable that we need to find. So I'm going to go ahead and find S of 5. And this is going to be 21 E to the negative K times 5. And then from here, S of 5 we know is equal to 19. And then solving this is going to require us to divide by 21. So we have 19 divided by 21 equals E to negative 5K. To solve this, I'm going to use a logarithm. I'm going to use ln, our natural log, and rewrite that on both sides and take the logarithm on both sides of my equation. And I have ln of 19 over 21 is equal to, and from our rules on logarithmic functions and exponential functions, we have that ln of e is just going to be 1, and so we're left over with negative 5k. From here I can divide by negative 5, and I will have k is equal to ln of 19 over 21 divided by negative 5. Substituting this into my calculator, we get k is equal to 0.02. And again, I'll change this to approximately equal to, and it does say to round 2 decimal places up above. So from here we know that our formula is going to be S of t is equal to 21, which was our S naught, e to the negative k, which was 0.02, and then times t. So that is our formula here. I'll go ahead and box this, and we can figure out how much we would expect the sales to be after so many weeks. And it does ask for us to figure out how much you would expect 8 weeks after advertising is in. So to do that, we're going to go ahead and substitute in 8 for t. We have 21e to negative 0.02 times 8. And then again, substituting this in on our calculator, we get 17.90. And again, remember that we changed our units to being in thousands. So I'm going to put down 1,000 units. And another way you can write that is 17,900 units. So again, either way is fine. Part B says, at what rate, so this time we're looking for R, should Josie expect sales to be changing T weeks after the advertising ends? What is the percentage rate of change? So in order to figure out this rate, we need to take a derivative. So we're going to find S prime of T, and our S of T function is listed up above in part A. And so taking the derivative of 21e to the negative 0.02t, we get 21e to the negative 0.02t times the derivative of the exponent, which is negative 0.02. Simplifying this, we end up with negative 0.42 e to the negative 0.02t. This is our function that we would have in order to figure out the rate of the expected sales to be changing T weeks after the advertising ends. And it says, what is the percentage rate of this change? And to figure that out, our percentage rate of change this is going to be our derivative divided by our function, and then times 100 to get that percent. So rewriting this, we have S prime of T, which is negative 0.42 e to the negative 0.02t, divided by S of T, which is listed up above again in part A, and then times 100. If you notice, your e to the negative 0.02 t's would reduce out. And again, don't forget you are multiplied by 100. And when you divide negative 0.42 divided by 21 times 100, we get negative 2. And so what this means is that sales are declining, because this is negative, at a rate of 2, and again percent, since this is a percentage that we already calculated, 2%, and we're measuring this in weeks, so per week. Right below this, it says, suppose you own an asset whose value increases with time. The longer you hold on to the asset, the more it will be worth. But there may come a time when you can do better by selling the asset and reinvesting the proceeds. Economists determine the optimal holding time for selling by maximizing the present value of the asset in relation to the prevailing rate of interest, and it's compounded continuously. The example on the next page says Jane owns a parcel of land whose market value T years from now is estimated to be V of T equals 20,000 e to the square root of T dollars. If the prevailing interest rate remains constant at 7% compounded continuously, when should Jane sell if her goal is to maximize the present value of the investment? So when should she sell this to maximize the present value of the investment? And so again, it does say that we are given, that says that she owns a parcel of land whose market value is estimated to be, and they give us a function there, and the prevailing interest rate remains constant, 7% compounded continuously. And we discussed present value back in chapter 4, but section 1. And this is in your notes on page 2. So if you go back and look at that, you can see the formula. So I'm going to go ahead and write PV for present value at time t is equal to the amount that we have. And for this case, we actually have a function. So we have V of t, and it's e to the negative RT. And so our rate here is going to be negative, and our percentage is 7%. So we have 0.07 and then t. Then substituting in our function, which is 20,000 e to the square root of t times e to the negative 0.07 t. We can combine these two because they have the same base, and our present value function is going to be 20,000 e to the, and we would add together those exponents. We have the square root of t plus and our negative 0.07 t. And since we want to maximize something, whenever we want to maximize something, we need to take a derivative. So we're going to take a derivative of our present value function. So taking a derivative of this, we're going to have 20,000, which is just our constant, e to the square root of t minus 0.07 t times the derivative of our exponent and the derivative of the square root of t, and I'll go ahead and write that up here. If you rewrite it as t to the 1/2, the derivative of that is going to be 1/2 t to the negative 1/2 power, or 1 over 2 square root of t. So we have 1 over 2 times the square root of t minus 0.07. And to figure out where this is maximized, we're going to set this equal to 0. From here, since we are multiplying, I'm going to go ahead and separate this by the zero product property. Say my first term, which is 20,000 e to the square root of t minus 0.07 t, is equal to 0. And then my second term here, I'm going to set this also equal to 0 and have to solve this. So the first one, this will never equal 0. And remember, if you were to go ahead and solve this, divide by 20,000, and then take a natural log on both sides, you will have that the natural log of 0 is undefined. You can also think of an exponential as never going to actually equal 0, so we're stuck there. Solving the second one, though, I am going to add 0.07 and then multiply by 2. And so we have 0.14. From here, I can multiply both sides by the square root of t, and I have 1 equals 0.14 square root of t, and then dividing by 0.14. To isolate t, I'm going to square both sides. When I square both sides, I get t is about equal to 51.02. And so this is where it should be maximizing, and if you would double check this, we know that our t values need to start at 0 since we are dealing with time. If I put on 51.02, checking to make sure we actually have a maximum here. If I were to substitute in something into my derivative that's smaller than 51, say 1, and then substitute in something larger than 51, say 100. And when I do this, I get that my first interval is positive, so it's increasing, and my second interval is negative, so it's decreasing. So it goes from increasing to decreasing. And we have and I'm low on room, but I'll put it down here in the bottom. We have a maximum at 51.02, so our present value is maximized at t equals 51.02. And again, we need to put our units on here. And so how are we measuring this? This is measured in time, and time in this problem is measured in years. So t years, if you look back up at the top. So make sure to put your units so you don't lose points. Right below this, we have what's called a logistic curve. It's approximately exponential at first, but it has a reduced rate of growth as the output approaches the model's upper bound, called the carrying capacity. For constants A, B, and C, the logistics growth of a population over time, X is represented by the model. The formula is written here and the graph of this is also given below. So if you notice, there is an initial value of the population. This is also a good one to use for different kinds of diseases and how they spread. And then we have a point of maximum growth, which is that inflection point. And so once we hit that, it starts to still grow. It's still increasing, however, it's not increasing at the same rate. And we hit a carrying capacity, which means that either there's no more land for people to live on, no more food for people to eat, and we kind of have maximized the number of people that we can have. Or if it's a disease, it's maximized out, it's infected enough people, and we'll start that herd immunity. So the next example that we have says public health records indicate that T weeks after an outbreak of a certain strand of influenza, approximately Q of T equals 20 over 1 plus 19e to the negative 1.2 T thousand people had caught the disease. Part A says how many people had the disease when it broke out and how many people had it 2 weeks later. So in order to figure out how many people had this when it broke out, time here would be equal to 0. And then 2 weeks later, and notice that T is measured in weeks, T would be equal to 2. So in order to figure this out, we have to find Q of 0 and Q of 2. So for the first one, substituting in 0 into our function, which is listed right up above, we have 20 divided by 1 plus 19e to the negative 1.2 times 0. And so when we do this, we get 1. And it's not just one person. Notice it's thousands of people. So we have 1,000 people. And again, you guys can write this as literally 1,000 people. 2 weeks later, we have 1 plus 19e to the negative 1.2 times t, and this time t is 2. So working this out, we get 7.343. And again, this is in thousands of people. So you can rewrite this as an actual number instead of with the decimal and the wording on there, and moving your decimal to the right 3 times because thousands has 3 times, or multiplying that number just by 1,000, and we get 7,343 people. So it did grow rather fast. So part B and part C we will look at together in class.